Okay, let's talk about indexes now and their impact on database performance. Now, this is an imagined collection right here of a bunch of documents, and the documents might have the form shown right here. This is a collection, and these documents might be on disk in essentially arbitrary order. And whether you're talking about mmap v1 or WiredTiger, there might be no particular order to the documents on disk. Now, if there's no index and you wanted to find all the documents where, let's say, name was Zoe, you would need to scan every document in the collection. And there could be millions of those. And this collection scan, or a table scan as it's called in the relational world, is just death to performance. It's probably the single greatest factor on whether or not your queries are going to perform well. More important than the speed of the CPU, more important than how much memory you have, is whether or not you can use some sort of index to avoid having to look at the entire collection. So how does an index work? What is an index? Well, an index is an ordered set of things. So imagine that we just had a simple index on, let's say, the name. And so if we had a simple index in the name, you can think of it as an ordered list of things. For instance, Andrew might be on the left because it's alphabetically early, and Zoe might be on the right, and in the middle might be Barry and Charlie, etc. And each of these index points has a pointer to a physical record. So it's going to have some sort of pointer to a location on a disk, or maybe the underscore ID for the document, so you can find the record. So Barry record might be right here, Charlie record might be right there, Zoe record might be right there. The nice thing about having something that's ordered is it's very fast to search it. Because if it was actually a linear list like this, and it's not in a typical database, but if it was linear like this, then you could search it using a binary search, and it would take you log2 of the number of items in this list. In real databases and in MongoDB, the actual way that this index is structured is called a B-tree. And looking at what a B-tree is a little bit beyond the scope of this course, but if you just go on Google and search for B-tree, you'll get to a great Wikipedia page that explains it pretty well. So you're going to want to put these indexes on the items that you believe you're going to be querying on, because that's going to make querying much faster. But sometimes we don't just want to query on, let's say, name. We also want to query on name and maybe hair color. So how would that work? Well, an index on name and hair color would be represented as follows. You'd write name, comma, hair color, and that's ordered. And if you did that, then all of the index entries would be ordered by name, comma, hair color. So for instance, there might be an index entry for Andrew, comma, blonde, and that's going to be a single index entry, which I'll represent by maybe making it green like this. And then there might be another index entry for Andrew, comma, red, and again, that's just one index entry right here. So we have another index entry here. And Andrew Blonde might refer to this document here. Andrew Red might refer to this document here. And then we might have one for Barry Brown hair. And then that's going to be right here. And maybe that points to over here. And then another one for Barry Red, which might be a document that is over there. And then in the far corner here, let's say I have another index entry for Zoe, and then let's say red. And maybe that document is somewhere over there. These documents, which I'll show you where they are, they're in the order of name, comma, hair color. So you can kind of see that if you wanted to find, let's say, all the berries with a certain color hair, you could do it pretty easily because you could, again, do a binary search for this structure and then do it again through this part of the structure to find, let's say, Barry with red hair. You could also do range queries. So you could say, find me all the berries with hair that's greater than or equal to brown and less than or equal to red. That would also work. But if, on the other hand, you specified just the hair color, you'd kind of be stuck, right? Because if I said, just find me all the people with hair color red, they're sort of all over the place, right? And they're not ordered in any particular way in this larger structure, so I can't use a binary search to find them. So as a result, whenever I'm using an index, I need to use a leftmost set of things. So if the index were, let's say, extended and included the date of birth, then I could search on just the name. That would work in this index, because then I could just do a nice little search. Or I could search on the name and the hair color. Or I could search on the name and the hair color and the date of birth. But I can't come in with just the date of birth or just the hair color, because then I have no way of searching this index. So let me review what I just said. If you have an index, and indexes are going to be described this way when we talk about them, of A, B, and C, then you can search on A, you can search on AB, you can search on A, B, C. C alone, no. C, comma B, no. And if you searched on, let's say, A, comma C, then it's sort of a partial yes, because it would use the index for the A portion and have to search through all of them on the C portion. Now, the other point I want to make is that indexing is not free, because whenever you change something in the document which affects the index, you're going to have to update that index. You're going to have to write it on memory and eventually on disk. Now, the indexes aren't represented the way I did linearly. They're represented as B trees, but maintaining these B trees takes time. So as a result, if you have a collection and you have indexes on that collection and the writes affect items that were indexed, the writes will be slower than if there was no index. That's right, indexing actually slows down your writes. But your reads will be much faster. Now, if you were just writing and you never wanted to ever find a document, you might not want to have an index, because then you could insert the document. It would be inserted anywhere on the disk. Wouldn't matter where, and there'd be no index to maintain. And in fact, one of the strategies when inserting a very large amount of data inside a database is to have no indexes on the actual collection at all, to insert all the data, and then after all the data is inserted, then add the indexes, and then build the indexes. That way you don't have to incur maintaining the indexes while you add data incrementally. Now, the fact that writes are slower and the fact that it takes time to update an index on every single write that affects anything in an index is one of the reasons why you don't just want to have an index on every single key in a collection. Because if you had an index on every single key in the collection, then you're going to slow down your writes more. And you're going to use a lot more disk space, too, to maintain those indexes. Now, I just want to point out that if you had 10 million items in a collection and there's no index and you search on something, anything, you're going to look at 10 million documents. And that's pretty expensive. And if you have to look at 10 million documents or 100 million documents and the amount of memory you have is much smaller than the amount of disk or space that the documents represent on disk, then you're going to wind up swapping all those documents through memory and creating a tremendous amount of disk I/O, which is going to be pretty slow. And this is why indexing is so absolutely critical to performance. All right, now it is time for a quiz. Which optimization will typically have the greatest impact on the performance of a database? You can see there are 4 choices here. Adding memory so that the working set fits in memory, adding a faster drive so that the operations that hit the disk will happen more quickly, replacing your CPU with a faster one, say twice as fast, or adding appropriate indexes on large collections so that only a small percentage of the queries need to scan the collection. Check the right answer.